Interacting with a large language model means engaging with a multi-billion parameter sorting machine. Professional workflows often treat these models as reasoning agents, yet the underlying architecture contains no facts and no internal database of truths. Operationally, the model functions as a sequential predictor. Take a simple text prompt. The cat climbed up the... To complete that sentence, the model calculates a probability score for every potential word in its vocabulary. In this instance, tree carries a 50% probability, followed by roof, wall, and window. The system selects the highest ranking option and appends it to the original prompt. From there, the process instantly resets. It takes the new, longer phrase, "The cat climbed up the tree," and restarts the calculation to predict the word that follows. This loop repeats word by word until an internal stop sequence is triggered. This multi-billion parameter calculation is the model's only actual task. Effective enterprise AI leadership requires viewing the system as a controllable statistical engine. Directing the model means manipulating this specific loop. This raises the question of how a probability engine recognizes conceptual relationships, knowing, for example, that emerald and green are linked. It solves this by translating human language into vector embeddings, which serve as multidimensional spatial coordinates. Inside a 3D vector space, conceptual similarity is physical proximity. Semantic gravity pulls related terms together, placing revenue, profit, and Q3 filing in the same neighborhood. Unrelated concepts inhabit different sectors. Panning across the map reveals a cluster where apple and banana reside. Because this map is multidimensional, it captures secondary meanings. Rotating the axis reveals a different gravitational pull, connecting Apple to Microsoft and iPhone. These relationships are defined by numerical arrays measuring distance. King and queen appear similar because their 1,536 dimensional coordinates are mathematically nearly identical. The system does not comprehend language. It measures the geometric distance between numerical coordinates in a vast conceptual galaxy. To use this at scale, corporations must build infrastructure capable of storing and searching these geometric coordinates. Traditional corporate databases struggle here because they rely on exact character matching. A traditional data searching for employee health benefits looks for exact letters, returning 0 results if the policy says medical insurance package. A vector database plots the query as a coordinate, expanding a radius to find the nearest conceptual neighbor. This is the role of a vector database. It acts as the high-speed storage for a company's proprietary PDFs, policies, and internal history. When the system retrieves these relevant documents and feeds them back into the model to guide its next token prediction, it completes the cycle of retrieval-augmented generation, or RAG. A vector database provides the conceptual memory required for an AI to recall and utilize internal corporate history. Dictating how this engine behaves does not require writing code. Product leaders use hyperparameters to manipulate token probabilities, enforcing either strict factual compliance or varied creativity. Temperature is the randomness dial, determining how strictly the model follows baseline probabilities. Setting it between 0.0 and 0.3 creates a narrow spike in the distribution, making the model highly deterministic, consistently selecting only the most likely tokens. Higher settings between 0.8 and 1.5 flatten the curve. This gives obscure, low-probability tokens a chance to be selected, generating more imaginative, varied output. To prevent high-temperature models from generating gibberish, we use top P, or nucleus sampling. It calculates the cumulative probability of top words and physically removes the rest, ensuring the model cannot choose a token that breaks the sentence structure. We also have tools to prevent the model from getting stuck in repetitive loops. Frequency and presence penalties apply a mathematical penalty to words that have already appeared. This weight pushes used tokens down the probability list, forcing the model to pivot to new vocabulary. Adjusting these hyperparameters confirms the system's nature as a controllable statistical engine, responsive to deliberate product constraints. We can see the impact of these settings by launching 2 distinct tools built on the exact same underlying model. The first is a compliance scanner, used to audit vendor agreements against corporate policy. For compliance auditing, we need absolute reproducibility. We set a temperature of 0.0 and a top P of 0.1, restricting the candidate pool to the most confident interpretations. This produces standardized results, ensuring every agreement is audited with identical logic. The second tool is a slogan generator designed for creative marketing brainstorms. For the slogan generator, we loosen constraints. A temperature of 0.9 and top P of 0.95 encourage exploring unusual word pairings. A presence penalty of 0.6 prevents repeating buzzwords, forcing fresh concepts in every paragraph. The functional gap between a rigid legal auditor and a creative marketer is bridged purely through math, using dials to constrain or expand choices. True AI leadership requires moving past the concept of a thinking machine and mastering the architecture of tunable probability. This mastery prepares us for the next stage, connecting this engine to your specific corporate context through retrieval-augmented generation.